This is the webinar series dedicated to bringing discoveries to patients. My name is Meena Lakshman. I'm the Applications Marketing Manager, and I'll be moderating this webinar. We will begin this webinar with some housekeeping information. There will be a recording of this webinar made available to you. During this presentation, all lines will be muted for the duration of the webinar. All right, and there will be a survey, a 3-second survey for you at the very end. We would like you to please take the time to give us a quick survey so that we can bring more of these tutorials to your attention. Please use any chat window at the right of your WebEx screen for questions. We will prompt you to provide your questions during the webinar. All the questions will be addressed towards the end. This webinar presentation is expected to be 45 minutes long with a question period at the very end. Right. It is my pleasure now to introduce our presenter today. It's Stephen Buttars. He is our product manager here at FUJIFILM VisualSonics. He comes to us to VisualSonics for 5.5 years and has an experience in application specialist. This position actually provided me an opportunity to interact directly with a global customer base, demonstrating and training users on all aspects of the technology. So those of you who've had the chance to experience his instructions over the years, you would be delighted to have his presentation today. Stephen has transitioned to product manager almost 1.5 years ago and is now responsible for guiding the development of the Vivo ultrasound imaging systems. All right, so Stephen, we will send you the privileges and let us begin the on-demand tutorial.
Great. Thanks so much, Meena, and thanks everybody for taking the time to join us on this tutorial. So for the tutorial, we're going to talk about a couple of different things, mainly focusing on the use of the VevoStrain analysis software. We're very happy to debut an updated version of the VevoStrain software, what we've kind of been referring to as VevoStrain 2.0. The software was updated back in the fall based on a lot of feedback and information, ideas and things that were sent to us from customers over the years. And we've tried to integrate a lot of the changes and suggestions into the software. So for the presentation, we're going to do a little overview of VevoStrain analysis software, what it is, what it's all about. I'll just mention a couple of things about its relevance and some recent publications. One thing I do definitely want to highlight in the presentation is image acquisition. Any sort of advanced image analysis, and you can really consider Strain to be an advanced image analysis software application, where you take your images, you capture your images on your animals in our case, and then dump them into the software and do the analysis on them. These sorts of post-capture image analysis software applications are very much kind of a garbage in, garbage out proposition, and so image quality of the images that you're actually going to analyze is very important. And then I'll switch over to the Vivo Lab desktop software, and we'll do a demonstration of analysis on a couple of images which have been made available to you for download off the website and will be included later on. So strain and strain rate analysis itself is a very valuable tool clinically for looking at a lot of factors, cardiovascular disease, cardiac regeneration, monitoring of potential cardiotoxicity with therapeutics, and looking at drug development. And it's been gaining traction slowly but steadily over the years clinically. We've had the ability on our system, 2100 platform, and now subsequently moving forward to the 3100 platform, to do strain analysis for some time. And we've seen over that time, I think around 5 or 6 years, we've had the application available. We've seen a very steady increase in interest, in use, and in papers being published, and really interesting results being teased out of the studies that our customers are doing. So this is just an example of what you might see for publications on the clinical side. I should mention, wherever possible, wherever we talk about a paper or a publication, I've tried to add the Pubmed ID number, so that if you're following along, taking notes, if you do see a paper that you want to look up really quickly, just rather than trying to jot down the author's name and the title, just quickly jot down the PMID number, and you can just pull the paper out of Pubmed fairly quickly and easily. So this paper here, just as an example, is a good example of what you might see, and some of the conclusions that they came to in the paper are that the changes in strain and myocardial tissue motion are associated with cardiomyopathy and cardiovascular risk factors, even in the presence of seemingly normal cardiac structure and normal functional parameters. Functional parameters being assessed with the more traditional measurements, the traditional approaches, such as the modified Simpson's biplane method of discs, or string method, or wall thickness measurements off of ultrasound. So you'll often see strain and strain rate analysis referred to as speckle tracking echocardiography, or speckle tracking or motion tracking. Speckle tracking is probably one of the most common terms, and that just is a derivation from the way the algorithm actually works to track the wall motion, which we'll see later on in the presentation. So, for the sake of comparison between VevoStrain analysis and the conventional measurements, of course, we have available the conventional measurements of cardiac function on the system integrated into our LV trace tool, which is a nice, fast tool typically used in long axis or short axis B mode or M mode to provide measures such as ejection fraction or fractional shortening, stroke volume, cardiac output, the traditional functional measurements that form the basis of most cardiovascular studies. It's able to track motion, it's able to look at changes in chamber volume, and it's sensitive to the larger changes that you would see in things like heart failure models, but we've often seen cases where in things like, say, cardiotoxicity or drug development models, you may get normal results from ejection fraction or fractional shortening or some other measurements, and where the heart is not functioning well, it's experiencing cardiotoxicity. So situations like that, teasing out these more subtle changes in myocardial performance are where strain analysis, really doing this speckle tracking analysis, really comes into play. Because it is a direct measure of the muscle contractility, it is able to pick up those subtle changes. And there have been some publications, this one was specifically done with VevoStrain on our system, showing that it is able to tease out those changes more earlier than the conventional measurements. So where an animal model may be well on its way down the road to experiencing heart failure, and that's something that with the conventional measurements you would pick up at a later stage. With the subtlety and the sensitivity of strain, you're able to tease out those changes much earlier on, and then obviously that drives your experimental design from there. This is just wanted to highlight the previous version of VevoStrain, the older version, provided some of the functional parameters. The newer version provides a full suite of functional parameters based on the LV long axis trace. Again, it's similar to a modified Simpson's biplane method of discs trace, but it provides the same typical cardiovascular functional parameters that you would normally be after in your studies, ejection fraction, fractional shortenings, et cetera, et cetera. So it provides just another method of generating those data on your animal models in the system, just through using strain. So for anybody who's heard of strain analysis, isn't really clear on what it's all about, it's just a really quick overview of what strain analysis and what really myocardial wall motion tracking is all about. So you're looking, when you're doing this tracking, in three axes of motion. The longitudinal motion in this direction, up and down the left ventricle from axis to base. The radial motion as the endocardial and epicardial borders come together and then relax and come together and relax, et cetera, et cetera. And then the circumferential motion as the heart, the cylindrical shape of the heart experiences that twisting motion going through its cycle, systole and diastole. So by tracking these borders, tracking the endocardial and the epicardial borders through a number of cycles, we're able to tease out data like velocity, displacement, strain, and strain rate, and shear in the longitudinal, circumferential, and radial directions. And you'll see when we get into the software that with just placing a trace and letting it analyze through a couple of cycles, you're able to tease out a really large suite of data on what's going on in terms of function through all these different planes of motion. So strain itself, if you think about it in sort of engineering terms, strain is really is tissue deformation. It's the actual deformation, the movement of tissue, and the strain and stress that's happening within the tissue, within the muscle fibers as the tissue is deforming. Strain rate is a derivation of that, where it's the deformation per unit of time. I would highlight this website. We have, full disclosure, we have no connection with the investigator that maintains this website. It's a great website for really in-depth mathematical explanation of the strain, the first order, second order strain, Green, Lagrangian, Eulerian strain components. It really goes in depth, and the investigator, professor that maintains this, provides some really great real-world analogies and explanations for what strain is and how it works and how it's assessed in the myocardium. So two other quick things I just want to mention too. Although the software, you'll see, has a great front end to it for showing the data and giving great examples, all of the data, because we are a research company and we know our customers are really focused on research, all of the data quantification produced by the VevoStrain package is exportable as multiple formats so that you can do further downstream mathematical analysis if you want to try MATLAB or scripting or anything like that on it. And within the software itself, it does provide a really nice representations, vector diagrams, parametric displays, and whatnot to really show you what's going on with your animal models. So I'll really quickly just highlight a couple of publications, and please do check our website, visualsonics.com, for other publications. We do maintain an up-to-date list of all publications related to the Vivo imaging platforms on our website, and you can drill down into that list to look at VevoStrain related publications, or even VivoVasc or Vivo Laser, all of the other types of imaging and analysis platforms that we have. So Pubmed ID number, again, I'll just highlight, is right here. This is a really interesting study looking at impact of high-fat diet, these transgenic mice being fed a high-fat diet and experiencing cardiac dysfunction. And they were able to show differences between the control and test groups, and very, very clearly, again, with VevoStrain, looking at some of the types of displays and data that VevoStrain shows, the parametric maps and the traces and whatnot. If you dig down into this paper and look, they were able to show very clearly, visually with parametrics and also numerically, that this high-fat diet that these mice were on in conjunction with this gene had a really significant effect on wall motion and cardiac function. Just moving ahead, another paper that came out just a short time ago. This is a great paper from a group at the Mayo Clinic in Minnesota that really shows a multi-area application of the entire Vivo imaging system platform, assessing the animal models with the standard measures, the LV trace measure of function, assessing the animal models with VevoStrain analysis, infarcting the animals, assessing them again with the normal measure and the standard measures, I should say, not normal, standard measures, and VevoStrain again after post-infarct, and then using the system to do guided injection of induced pluripotent stem cells, and then assessing the recovery of the damaged myocardium from the intervention of the induced pluripotent stem cells. So a really great paper that really shows a good all-around story of an application of the Vivo imaging systems. So definitely I would recommend having a look at this paper if you're interested to see not only what you can do with VevoStrain analysis, but also what you can do with the Vivo imaging systems generally. So 4 papers here in a list. These are very recent 2013, 2014, 2015 papers that have come out where VevoStrain analysis was used off of off the Vivo imaging system platforms across a range of animal models. We've got a paper that was looking at rabbit model, and the rest, I believe, are mouse. Yeah, the rest are mouse models. Again, looking at functional changes. A number of the papers use the speckle tracking term that we talked about off the top. So if you're doing literature searches, that's definitely a term to look for. I would recommend, again, if you want to see the sorts of work that's being done with VevoStrain analysis where it's being applied, do take a look at these papers. And again, you can find the list on our website. So they're all really great stories to show where the software can be applied in research. So moving on, I want to highlight some of the changes that have been applied with this new version of VevoStrain, this updated version of VevoStrain. And starting right off the top, so I'll try to keep, for those of you who've never seen VevoStrain or never used the VevoStrain analysis software, I'll try to keep the workflow, and I'll highlight when I actually do the analysis live. I'll highlight the workflow and point out a couple of changes. For those of you that are familiar with Strain, the screen will look very familiar. This is the initial anatomical M-mode tracing screen. We have a nice addition now where the desired window of the cycles that you want to analyze can now be automatically selected based on the number of R waves. So you can actually plug in the number of R wave cycles here that you want to analyze, and then the system will automatically choose that number of cycles based on the R waves that are present. And as you add or delete R waves, the window, the size of the window that you set will slide forward or backwards. And I'll show this again when I do the live analysis. But this just really speeds your throughput. Previously, you had to grab this window at the side here and sort of slide it in, and grab this window at the side and slide it into where you wanted. Or you ended up, if you didn't window it down, you ended up analyzing 6 or 8 or 10 cycles, which is really, for the amount of data that VevoStrain analysis generates, is really a lot of data. So this just helps you, helps with your throughput, with selecting data, and then also, again, with having to manage the amount of data that you're using. This is an example of what the main analysis screen looks like. So we have traces, curve traces. We have parametric maps here with selections at the top to look at velocity, displacement, strain, and strain rate. I wanted to highlight the addition down here that I mentioned of a full suite of cardiovascular functional parameters that have now been added. This list was a little bit thinner before in the previous version. So this has actually been beefed up a little bit now to give you a full suite of stroke volume, fractional shortening, ejection fraction. And we also have a new addition in the software, this new number of global longitudinal strain, GLS, which is a single measure of strain based on the entire trace. So the global longitudinal strain would take the full trace from beginning to end in and look at the strain longitudinally. So longitudinal strain is going to be the strain from point to point to point to point down the trace here, all the way around. That global longitudinal strain number is derived from that, and it just provides one simple short number across the entire trace to give you an idea of a threshold of where your models are, if they're at or below or above a certain threshold that you're looking for in your studies. This number, this GLS and measure, has been gaining some traction on the clinical side, and so we decided that it would be really appropriate to add it into this updated version of VevoStrain. Now this is a long axis analysis view. In the short axis analysis view, the number that's reported here is GCS, Global Circumferential Strain, and it's based on the same concept, just one number for the strain across the entire trace. In the subsequent screen from the main analysis screen, the time to peak analysis screen, or the segmental synchronicity page as it's titled, we've added some changes here. One change is an increased ability here to look at different cycles, again, based on the R to R timing. The parametric segmental synchronicity images that are shown here, these sort of C-shaped images, these are based on taking all of the points in the trace and chunking it up into 6 chunks, and then looking within one cycle at the maxima, at the peak velocity or peak displacement or peak strain rate, depending on which radio button you have selected. But it may not be appropriate in some situations to only look at one R to R cycle, that first R to R cycle. You might want to look at the middle one or the third one, or you might actually want to put glue all three together and average them out. And so we have the ability to do that now, where it was actually quite challenging to do that accurately and reproducibly before. Now all of the selections here in the cycles are based on the R to R timing, and so you can skip forward and backward. And again, I'll show that in the live demonstration when we get to that. The export is probably one of the biggest changes. We now have a new export format that's available. The option now to export directly to an Excel spreadsheet. The previous version, you could only export to a CSV, a flat text CSV file, which was really represented just a big dump of all of the data that was generated in the strain analysis, and it was not terribly well organized, and it could be hard to read, especially for larger studies. So we've organized the data now into Excel spreadsheets, so that when you open the export in Excel, it opens into a really nicely formatted sheet. It has really well organized tabs and labels and headers and whatnot that allow you to really dig down quickly and easily into the data and try to tease the numbers out. Now, for anybody who wants to do sort of large-scale processing, like doing like 30 animals and exporting all of them and then trying to parse the data out with, again, scripting languages like, say, MATLAB or Python or something, we do also have the option to export this new format to CSV. And because we recognize that some customers were doing that sort of scripting approach with the old version of VevoStrain, the old version of the export is still available. So don't fear that your scripts that you worked long and hard on have been broken. The old format is still there if you do want to continue to use the old scripts that you may have written and not update them. So I wanted to highlight something that's a little bit separate from the topic at hand, VevoStrain, but is actually a really important distinction to make. Vivo Lab Workstation. So previously, in the earlier versions of the 2100 software, our workstation was always just referred to as the workstation, as the 2100 workstation or the laser workstation. We've actually broken that connection now and have rebranded the workstation as Vivo Lab, and we've laid it out now as its own item, its own piece of software, and it's designed to replace the existing PC workstation, and it's also designed to work with all of our imaging systems. So not only the 2100 laser system, but also our Vivo 1100 low-cost entry-level platform, and then also our Vivo 3100 platform that we released last year, our touchscreen-based ultrasound acquisition system. So there is an update to the workstation, to Vivo Lab, available for download on our website, on the customer portion of our website. It's actually being posted today for download. It's version, if you want to write it down just to compare the version number that you might have, the current up-to-date version of Vivo Lab is version 1.7.1, and that version has the newest VevoStrain release that we've been talking about here today and that I'll demonstrate. So the Vivo Lab workstation release, for anybody who has the workstation already, it is a free upgrade. It's downloadable on our website. Just download it, run the installer, and it will replace your pre-existing workstation. The VevoStrain update that's encapsulated within the Vivo Lab update is also a freely available update for anybody who already has VevoStrain. So if you have VevoStrain enabled on your workstation dongle, grab the new version of Vivo Lab off our website, install it, and you'll be up and running with not only the new version of Lab, but also the new version of VevoStrain as well. I guess I did mention, but one thing again that's important to really highlight is that Vivo Lab is now a unified platform. So for anybody who's using a 2100, a laser, anybody out there who may have one of our new 3100 systems or one of our Vivo 1100 systems, Vivo Lab is compatible with data from all of those systems. Regardlessly, it is not compatible with Vivo 770 data, which I'm sure is a question that some people might have. The Vivo 770 image data is in a very different format from our current format, and the Vivo Lab is just not able to be updated to handle that format. So for 770 users out there, the Vivo 770 workstation still stands as the offline analysis package for the 770. So I did mention that I wanted to talk about image acquisition, and one of the really critical things, again, just to highlight, with these powerful post-capture analysis platforms, image acquisition, quality images, good image acquisition settings are really, really important. It is really kind of as the old software programmers say, garbage in, garbage out sort of proposition. If you have images that are a bit sketchy, they've got some artifacts in them, and you try to analyze them with something that is as able to pick up such subtle changes as VevoStrain, you may get really questionable results out of those analyses. So just to highlight a few things on image acquisition, the choice of the quote-unquote proper transducer is really critical. You have to consider the attributes of the transducer with respect to the subject animal or model that you're imaging. So each of our transducers has a number of attributes, such as the center frequency that it transmits at, the maximum frame rate, the maximum image depth, width, field of view, the maximum Doppler cutoff that the transducer is able to measure, resolution. All of these things are really critical attributes for the transducers. We have available on our websites, or you can email anybody at support and ask if you would like an updated transducer chart, transducer reference chart that provides all of the major numerical specifications for the transducers, and also provides some suggested applications. So as an example here, the MS550S transducer, it's a 40 megahertz, so it's very high frequency. It's a shallow focus transducer, so it's very good for imaging smaller animals, for looking at sort of more shallow and sort of mid-depth objects. Embryology comes to mind as a good application. Carotid imaging, carotid wall imaging is another good application for the 550S. The 550S in abdominal scanning really shines in pancreatic imaging, looking for pancreatic tumors. So very specific application, whereas on the flip side, you wouldn't want to try to do cardiology on a rat with a 550S because you would actually have difficulty even seeing the posterior wall of the heart in a rat because of its depth. So again, really proper transducer choice when designing your studies. Again, on the system, choice of the application and the preset is really important. So this is a Vivo Laser Vivo 2100 panel. It's a little bit different on the 3100, where we have applications that are more animal anatomy, target animal anatomy specific. And the list on the 3100 is maybe a little bit more obvious. When you plug in an MX550S on the 3100, you're presented with a list of, say, small mouse cardio or small mouse vascular, so it becomes a little more clear. On the 2100 and laser platforms, you really just have a choice of the application, cardiology or general, and then within that application, there's a range of presets. Now, one thing to keep in mind with the presets is that the factory defaults are there to form a basis, a foundation, to give you a guide, but it's very useful to create your own presets specific to your animal models or your target anatomy or design of experiment. And pretty well anything that you see highlighted in this box here that's adjustable on the system can be saved as a preset. So you can change your gain, your width, your depth, your line density, and a variety of other things that can all be saved in as presets. So this really allows you to tune the acquisition settings to, again, your animal models and your design of experiment. And one last thing to highlight, it's really important of all of the settings, I always like to highlight the gain. The gain setting is really important because it changes the underlying data in your images. It appears to make the images either brighter or darker, and it actually does change the underlying data as opposed to things like the display map or the brightness and contrast, which are really, they can be changed at time of acquisition, but they're really more of a post-acquisition kind of image processing type adjustment, and they are reversible, whereas the gain is not reversible. So you want to make sure definitely when you're capturing images that you're not overgained or undergained, because that will impact, again, the quality of your images, which subsequently impacts analysis that you might conduct on those images. So talking about image quality, so I've got a couple of examples here. This is what I would term a quote-unquote poor or poorer quality four-chamber image. This is from a mouse with an MS550D. And you can see some examples of some things that are causing problems with the image here. The left ventricle is right here in the image, but it's really hard to see. There's a little piece of the intraventricular septum there. We've got some sternum shadow blocking. We've got lung shadow on both sides. We've got a reverb artifact that's across here, which is probably from too much gel standoff above the animal. And also down here at depth, we've got some noise which might be caused by overgaining the image a little bit. So all this excess background gain noise can obscure the anatomy that you're interested in looking at, and then subsequently with something as sensitive as speckle tracking in VevoStrain can actually mess up the tracking as well. So really important to try to eliminate these artifacts with animal positioning, to shift the sternum over, quick imaging so that the animal's lungs don't have time to balloon up while they're under anesthesia if you're using it, watching the amount of gel standoff that you've got so you don't get these reverb artifacts or even these weird sort of slash-like grading lobes that come in from the side sometimes with too much gel, and really watching your gain settings, not only the global 2D gain, but also the time gain correction profile down here. So this overgain in the bottom could have been corrected by just bringing the gain, the time gain correction, the TGC sliders down a little bit here in the lower portion. So a more quality image would be an example of this one here. This is a short axis image, so you can see the left ventricle really well highlighted, anterior and posterior. Little piece of the posterior papillary muscle there, intraventricular septum, a little bit of the right ventricle. We've got a bit of lung shadowing in here, but we've positioned the animal and the transducer such that it's not impacting the anatomy that we want to see. And again, our gain profile looks pretty good here. We're not really seeing any artifacts or overgaining or undergaining here. So this is a nice clean image, what I would call, again, a quote-unquote good quality or better quality image. This is one that I would say is acceptable for analysis in something like VevoStrain because, again, we can see the full endocardium, we can see the full ventricle, we can see the full endocardial border, and we can do some nice speckle tracking on that image. So speaking of speckle tracking on images, let's switch over now to the Vivo Lab software with the new updated VevoStrain analysis platform in it. I have two Vivo 3100 images that were captured with an MX550D, one in long axis and one in short axis. So I'll run some analyses on them. If you feel like I'm going too quickly when I'm placing points or anything, just remember you will receive a download link for the recording of this webinar afterwards, which you can then review at your leisure. If you think, oh, he went too fast there and I missed what he did or where he placed those points there. So you will have the opportunity again to review this later on. And also at the end, obviously, we're going to take questions too. So if there's something that you're really stuck on and not sure about, feel free to ask questions, and I can always pop back into the application and just show you. So I'm just going to switch over to the Vivo Lab. Your screen may flicker a little bit there. And so we've got the Lab platform. I should actually point out now, again, this is version 1.7.1 of Vivo Lab, and so if you are updated, you will see the Vivo Lab branding up here in the corner instead of Vivo 2100 or Vivo Laser as before. And if you are wondering about what version you're running, you can always go to the Help, which is right over here where this question mark is. Older versions, pre about I think 1.6, had a big button up here on the top that said Help. So if you don't see the question mark, look for a Help button up here on this toolbar, and that's already an indication that you're running an older version. If you go into Help, click on Help, you'll get this pop out here, click on About, and this will take you to the Help About window. What you want to do is look in the upper left corner here, and you'll see the version, the build number, and the build date. So 1.7.1 is what you want to look for. There's a variety of other information that's provided on this Help About screen as well. So good idea to look there once in a while and see what there is to see. So we'll have just a quick look at the image again. So this is an image from the Vivo 3100 platform in long axis with a 550D, and I'll go to the measurement panel here, and we'll go into VevoStrain. You can get into VevoStrain either from that button on the measurement panel that I just clicked, or there's also a strain button on the top toolbar in the study browser, and I'll use that one when we go into the short axis analysis window. So what will happen is the software will export the data, the image data out, and import it into Vivo Lab, and then you'll be presented with the initial Vivo Lab screen here. So this is what I call the anatomical M mode, or the AM mode analysis screen. I'm just going to brighten this image up a little bit just so that we can see the anterior wall a bit better. I'm going to place an anatomical M mode line down here, and I'm also going to reverse the black and white, because I like the reverse view better. It just seems to be the way my eyes work. I like a black chamber better than a white chamber, so it's a little easier for me to see where the walls are if I'm looking from black to white instead of from white to black. So I already have 3 cycles selected here on the right side, and you can see that we've already got 1, 2, 3 cycles selected here instantly based off of the first R wave. Now, if for whatever reason I don't like this window, I want to move the window over a little bit, I can hover over an R wave, I get a little X, and I left click to delete that R wave. As soon as I delete the R wave, the entire window slides over to the right. And I can keep pushing it, I can push it all the way over, or I can actually double click out here, single click, and bring the R wave that I deleted back. Obviously I put that in the wrong spot, I didn't want it there in the first place, so I'm going to delete it again, and my window will slide over here. This setting of cycles is what I would call sticky. I believe it's blank the very first time you go into the application. Once you set it to 3, it will stay as 3 or 2 or 4 in subsequent times when you go into the software, but then you can always change it again, and then it will stay kind of sticky again. So you've got the ability to kind of play around with it a little bit. If you find that you want to maybe analyze 4 cycles instead of 3 or instead of 2, you can always change that. I typically do 3 just because 3 is kind of a nice number that I like. So after clicking next, we're presented with the tracing screen. We have to tell the software what type of tracing we want to do. We want to do a long axis, a short axis, or a free curve. I should mention free curve is pretty much just like it sounds. It's a single line, curve that you're able to put just about anywhere on the image if you see a line. I actually made free curve work on rat diaphragm one time, just because we were kind of interested with a group that wanted to see muscle stress in the rat diaphragm. So pretty well any area where there's a nice distinct line of tissue that's moving, you might actually be able to track it with the free curve. So I'm going to click on long axis. Again, those of you who are familiar with Strain will see a big difference here. The tracing screen is substantially larger. Before it was just a small tracing window that was kind of jammed up into the upper corner. And we also have the physio data, the ECG trace from the system here, and with a marker showing where we are, so that if you want to do your tracing on a particular point with respect to the PQRST cycle, you can now actually choose a specific point. So if you wanted to trace right off of a particular wave, off the P wave or somewhere else, you're able to do that now, whereas before you were kind of working blind. You really didn't have reference with the ECG tracing exactly where you were in the cycle, frame to frame. Now, it's just me. I typically like to trace kind of somewhere in the middle between systole and diastole, not full systole but not full diastole. So I'm going to choose this frame here to trace. Now, the tracing that we do here is really a seed tracing. So this provides the software with a guide for where it should start to look for speckles in the edges and start to do the tracking. So I'm just going to start clicking, placing points. You'll see I'm placing the endocardial points, and the epicardial points are popping up and following me in kind. I should mention here that this is where I typically start and stop my tracings in VevoStrain. If you look back, if you've been familiar with VisualSonics for a long time, if you've used Strain before, if you look back into some of our older collateral, you might see, with respect to VevoStrain, you might see the traces extended right out to the base on the anterior and the posterior. And that is the way that we used to approach doing the traces. In subsequent years, we've discovered that that may not really be appropriate. The tissue that's up here next to the RVOT and down here next to the mitral valve, the septum and the atria, move differently when compared to the rest of the tissue in the myocardium, the rest of the myocardial tissue throughout the ventricle. So we've subsequently, at least I have anyway, started to kind of pull the ends of my traces in VevoStrain back a little bit to try and avoid some of these potentially confounding factors that are a little bit further up, closer to the base. You can, once the trace is placed, you can globally, with these little plus-minus icons here, move the trace in or out. So this will move the epicardial trace in or out overall, and then you can actually also move individual points as well. So I'm actually going to hover over a couple of these points that are down here at the apex, and I'm also going to pull a couple of these points in here that are a little closer up to the anterior RVOT IVS layer. One question we get often with VevoStrain analysis is how many points should I place? How many points should I place here when I'm doing my seed tracing? It actually doesn't matter. As long as you trace the border fairly well and you're comfortable with the shape that the contour has taken around the border, the software will fill in the gaps. So any trace in long axis or short axis, no matter the length, no matter if we started here or here, no matter if we ended up here or down here, it will be 48 points long. So the software always divides the trace up into 48 points, and it just takes your seed points that you've dropped as guides as to where to start. So really you can get away with, I've done tracings multiple times with only maybe clicking 3 times across the anterior, once at the apex and 3 times across the posterior, and then just clicking over here on the little rainbow icon to start analysis. And even with those seemingly few points, 5, 6 points, the tracking will often come out to be quite good. So that's something that I wouldn't really get too hung up on when you're doing your analysis in the software. So we click on Start Analysis, and the software will kind of chew on the tracing that we've done a little bit, and this is what we come out with in our main analysis screen. So I'm just going to turn on the vector display, which is over here on this little circular icon. This gives us a nice display now where we can see in terms of how the velocity vectors are moving through the 3 cycles that we have analyzed here. Now we've got a lot of data on this screen. We've got the radio buttons across the top for velocity, displacement, strain, and strain rate. And we've got blocks here. The upper block is the radial, and in this case velocity. So the attribute here, velocity, is dependent on the radio button that you've chosen here. So if I choose strain, now we've got radial strain. And longitudinal strain down here. Now, if we had done a short axis tracing, and you'll see it when we do one, this will be circumferential. So you'll always have radial up here, provided that you do an endocardial and epicardial tracing. If you unchecked the checkbox here in the tracing screen where it was checked endo plus epi, if you uncheck that, you'll only get the endocardial tracing. If you only do the endocardial tracing, you won't get a radial component here, which is, again, that's a change in this software. The previous versions would always give you an arbitrary radial component if you only did the one tracing. Now, if you only do the one tracing, we just don't give you that arbitrary component. We didn't think that was really a valid way of doing things. And we've, by default, put the endo plus epi checkbox on so that now, unless you actually don't want to do the epicardial tracing, you're going to get both components, the radial and the longitudinal. I should also mention here that with the, actually you can see it with the strain or the velocity. You see a tag down here that says longitudinal strain in the endocardium. Over here, we have our tracing history, and we can flip between the epicardium and the endocardium. So now we see longitudinal strain epi down here. So what we have selected here for our tracing, and you can do multiple tracings. Actually, I'm getting ahead of myself. I'll get to that in a sec. So what we're displaying now here, if you think about all of the data being displayed on this screen in these curves and in these heat maps, you've got radial and longitudinal, sometimes just the endo or epi, sometimes just the strain or strain component itself, endo or epi, velocity, displacement, strain, or strain rate. So you've got a significant amount of data able to be displayed here. The curves here, I mentioned that the tracing here is divided up into 48 points. Each of these curves represents one of those 48 points. And as you hover over them, you can see a little tag that pops up that gives you the time point and the strain for that particular point. If I go to the velocity radio button now, and I hover, now I'm getting the time point in milliseconds and the velocity figure in, you can see the scale over here is in centimeters per second of that particular point that I'm hovering over. The heat maps here are visual representations of what you're seeing in the curve data. So you can see here, as I hover my pointer over, I'm going to take, just temporarily, I'll take the vector display off and I'll pause this so that it's not moving around so that we can see. If I hover over these heat map areas, you can see up above, we've got only a single tracing being shown now. That is the tracing that relates to that point where I'm hovering right now with my pointer. We've got a vertical line, that's the time point. So all of these graphs are always milliseconds time on the x-axis, and then the y-axis varies a little bit. In this case, we're looking at velocity, so it's centimeters per second. And I hope you can see on the endocardial border tracing, there's a blue dot that's moving there now. And that's following, that blue dot is following my cursor as I move up and down the heat map. So what we're able to do here is, if all 48 points are too much to analyze, and you're only interested in teasing out a few small areas, a couple of points, we can actually manually set, just by clicking, a few of our own points here. So I can go through here and set 5 points, 2 in the anterior, 1 at the apex, and 2 in the posterior. I can also do, you can actually see a point that's following my cursor here. I can do it on the tracing as well. Now what we're seeing is, on the graphs here, is the display of the curves for only those points. And again, radial velocity in the endocardium here. If I were to switch to strain, we would now see the radial strain or the longitudinal strain in the endocardium being displayed for those individual points that I set. So this allows you to really filter out some of the massive quantity of data that the software produces, and have a little bit more control over what you're actually looking at. We can reset the display right here. That will clear out our points that we set previously and take us back to what we were set at as the default. Some other areas to highlight here. I mentioned in the lead-in presentation this area here that provides your cardiovascular functional parameters, stroke volume, fractional shortening, ejection fraction, global longitudinal strain here. We have a graph down here in the bottom that plots volume by time, and also the change in volume by the change in time, the derivation of that. So very informative area here to look and see as the volume is changing with respect to time. You can tell that this is a normal animal because the curves are nice and clean, and the volume is really changing appropriately, as one would expect with the time that we're going through. Lots of functions available over here in the tool bar on the right side. I mentioned the export. There's a lot of functionality to export AVIs and pictures if you're doing layouts for papers, posters, presentations. If you want to do AVI movie exports for PowerPoint presentations, things like that, it's all doable here in, and I should say, multiple formats. If I just click on the picture format, JPEG, bitmap, TIFF, lots of flexibility there. A really key point with export is this regional data export in a variety of formats. The old format that I mentioned, so that's the old format, flat CSV, and then new format, straight to Excel, or to a flat CSV, but that is formatted with the new updated format. And I should also mention, actually, that one other thing this new format does is not only provides much better organization, it also corrects some oversights in the old format where there was some data missing out of the old export format. As far as we can tell, and we've gone over it with a fine-tooth comb, all the numbers that are presented in the software in both analysis windows are now committed to the export file as well. So you have all of your data at hand there. A couple of other things. You can do more traces, so you're not restricted to just one trace. You can do multiple traces on the image, and as you do more and more traces, this history window will fill up here. You can always go back if the tracking is kind of poor. You can always go back and edit a trace. One thing that's available now that was not available before is, previously, if you edited a trace, but the edit actually turned out to be worse than the original tracking, you had no ability to go back. There was no undo function. Well, there is now. If you go to edit, rerun the analysis, and then you don't like it, there is actually, on a rerun analysis off of edit trace, when you come back into this main analysis screen, there will be an undo button right here by the history, and you can actually skip back to the previous tracking that you had. It's a nice ability to go in and step back. I should just move ahead now to the next screen in the software, which is the time to peak. And this is the screen that I mentioned where the system is now taking, the software I should say, is now taking all of those points, all those 48 points, and chunking them up into 6 sections, and then providing peak data. So right now we're looking at the peak percentage in strain and the time that peak occurs in these different segments. You have control over here to look at different curves, so you can add and remove different curves if you only wanted to look at certain segments. The improved analysis over here is really nice now, where, as I mentioned in the lead-in, all of these data, these peak data here and this display is just based on this one R-to-R cycle, and you can see the red window here. So we can actually skip around to different cycles in the analysis. We can also add, if we wanted to, say we were in the middle and we thought, oh, well, that one, I want to average my data. We can actually add the one to the left, and we can add the one to the right. We can continue adding. We can add all of the R-to-R cycles here and have the software average the data for the peak, in this case, percentage strain and peak time that it occurs at across all of those cycles, or just reset it back to the first one. And as with the main analysis screen, your displays here change as you change your radio buttons. So again, here we've gone to velocity. So now we have the radial velocity and the endocardium. The parametric segmental images have changed here, and now the data here is showing the peak velocity in centimeters per second and the time that peak occurs at. And again, also as with the main analysis screen, you have over here on the right side the ability to flip between the endocardium and the epicardium as well. So again, as I said with the main analysis screen, lots of data being produced here. Radial, longitudinal, endocardium, epicardium, velocity, displacement, strain, and strain rate. The data are segmented up into these nice sections, but again, it is a lot of data. Also exportable, again, as JPEG flat images and improved data export format here in this screen as well. I think that is about it for the long axis overview. Okay, I'll pop back out here really quickly to the short axis, and we'll jump into VevoStrain directly from the study browser. One thing I should have shown, I just realized it now, is another nice addition in this new version of VevoStrain is you actually have the ability to do multiple image analysis at the same time. Whereas with the previous version, you could only do one image at a time, and then you had to jump out. We can actually do multiple images. So if I have these two images here, I can select them both, click on VevoStrain. They'll both be pushed into VevoStrain, and you'll have an extra icon that shows up that gives you the ability to switch back and forth between the images. I can't remember what the upper limit is. It was either 4 or 6 images at a time. I think we figured that we can handle based on memory usage. So I think that's about it for the overview of the strain analysis. Are there any questions on what we've seen so far today?
All right, thank you, Stephen. There's about a couple of minutes for us to take on questions. There is one that has come through. Stephen, function can be measured in M mode, LV trace, and now VevoStrain. In your experience working with customers and their publications, which package is most reliable?
I would say that it's a design of experiment question. The traditional measure of short axis M mode function is great for an application where you're looking at global changes, say something like drug screening, cardio tox, something like that. But if you're looking at an infarct model, if you think about what M mode is a single line, a single A line, out of a single plane of view, based with a bunch of calculations and measurements done on it. The calculations on it are based off of an assumption of a 2-to-1 length to width ratio of the ventricle. Well, if you're looking at an infarct model, plus or minus a millimeter in your plane of view, you could be off the infarct, on the hinge point between the infarct and hyperkinetic tissue, or right on the infarct, and you're going to get drastically different functional data from that measurement that you do based on all those assumptions. The long axis LV trace takes in a lot more of the heart when you're doing the measurements. It's a great application again for cardio talks, but it's much, much better for regional changes, again, infarct models, something like that. Where strain comes into the picture is, I think, really its sensitivity. If you've got massive changes going on, massive hypertrophy from a banding model or massive infarcts, where you've got a third of the heart that's been infarcted and the other 2/3 are hyperkinetic, you'll definitely see, you'll get lots of great data out of VevoStrain, but you're probably able to screen those animals with a standard LV trace measurement as well. But if you're looking at really subtle changes, those early changes that happen with exposure to drug, with changes, maybe changing a gene, and then as the animals develop, their heart function changes, those early changes are where VevoStrain really comes in. Now, you can also make the argument, too, that VevoStrain provides one nice centralized platform as well, where you've got your functional data and your strain and strain rate data all combined into one platform. So I think that's something to keep in mind. But I really think it is dependent on design of experiment. What are your animal models? Even where are you trying to publish sometimes? Because sometimes there always seems to be this requirement for a short-axis M mode when it may not be the most appropriate thing, and sometimes that's journal dependent as well.
Absolutely, Stephen. There are a couple of more questions. While we're taking questions, we're also going to put up a survey for you guys so that you can give us feedback. These are educational webinars. The other question that's with regards to good heart rate or good ECG tracing, for a mouse with a heart rate of 500, what frame rate would you recommend? Especially if you want to do both strain rate or strain measurements and then systolic and diastolic strain rate. What is your recommendation? We're
going into VevoStrain, the higher you can get the heart rate, the better. Now, higher heart rates on the imaging system are dependent on a number of factors. Transducer selection is really key. The applications and presets for cardio scanning are already set to have a single focal zone, which will bring your frame rates way up. One of the things that you have when you're scanning live that you have a lot of control over is the image width. And by bringing the image width in, you can drive your frame rate up. So one thing to keep in mind is, especially depending on how you're going to do your tracing in VevoStrain, if you kind of follow the method that I showed where we start a little bit in from the base and we stop a little bit in from the base, well, you don't really need the whole base or the aortic outflow tract and the apex in the image if that's the type of tracing that you're going to do in VevoStrain. So you can trim a few millimeters off the side of the image, recenter the heart, and just get a really good high frame rate image of just the area that you want to trace in VevoStrain. Keep the image maybe a little bit wider for your more functional measurements like your LV trace in B mode or other measurements that you might want to do. But if you're really focusing on good quality tracing in VevoStrain, the heart rate is really key, and that's especially a factor when you're imaging rats and larger rats. As you go down in lower and lower frequencies with our transducers down to the 21 or the 15 megahertz transducer, the image width is quite a bit greater, and it does tend to drop the frame rates down a fair bit. So if you're imaging, say, large rats with one of the 201 transducers, really be conscious of how wide the image is and what your frame rate is. You don't want a frame rate that's lower than 120 frames per second for those low frequency, lower frame rate images. Try to squeeze the image width in and drive the frame rate up as high as you can. But the strain software itself is able to cope with very high frame rates. I've seen people doing semi-conscious scanning on animals that were 600, 620 BPM, and the software was still able to track the edges through the cycles.
Very good, Stephen. That obviously goes to the next question. What's the lowest frame rate that it can go, highest frame rate, and then how do you optimize the frame rate that you can acquire, that you can use strain with, right? And that's the image width, keeping that strain. So there is also another question like ECG tracing, having a good ECG tracing, having good frame rate, having that image width, but having the right image width in the center of the field of view. Any influence with gels? You know, you have shadowing and those kinds of situations, especially with different types of models. Is there any way, have you seen people use different types of gels? This is one of the questions that came through. If that has any effect?
Yeah, in any kind of ultrasound imaging, preclinical or clinical, your ultrasound gel is your best friend and can sometimes be your worst enemy. If too much gel standoff, so too much gel between the face of the transducer and the subject animal, can lead to a couple of different things. It can lead to some weird artifacts in the images, like that reverb artifact that I showed, grading lobes, some of these weird sort of angular slash things that come in from the side. Air bubbles in gel are image quality killers. We even go so far in some of our imaging modalities, specifically in our Vivo laser photoacoustics imaging, we actually spin the gel down in centrifuges. And we have a number of other customers who, just for their regular day-to-day ultrasound imaging, they actually centrifuge their gel to try to get all the bubbles out of it. I tend to like gel that's a little bit thicker. I find with the heated platform underneath the animal, and sometimes using a heat lamp above, the thinner gels tend to melt and kind of run around a little bit, but that's just me. I know other people, I know one of our application scientists specifically who likes to use thinner gel and likes to have the transducer almost right down on the animal's skin and have almost no standoff at all. So work with it. I would say work with it and try different gels. There's a wide range of viscosities of gels that are available, and if you're finding, depending on how often you image, like if you only image for a week and then everything sits for 2 weeks or 4 weeks or whatever, if you're on a time course, as that gel sits, the air bubbles can form in the gel. So it's not a bad idea to maybe try spinning your gel down and try to get rid of some of those artifacts. Keeping the animals cleaned off as well too. Make sure to get the fur out of the way, because the air that gets trapped in the fur can be a real confounding factor as well.
Absolutely, absolutely. Yeah. We are 8 minutes past the hour. I really appreciate everybody's attendance. We have 2 more questions, very quick questions. Stephen, on the analysis software, there's the use of what is the use of the reverse strain button? That's number 1. And what does accuracy mean in the analysis window? While Stephen is answering this question, if you can click on the survey link to, so that we can get your feedback. Stephen, with respect to the software.
The accuracy gives you, it's been a while since I've been asked that one, but I believe it's related to the standard deviation across the averages of the particular factor that you're looking at. So you'll see the accuracy change as you go from strain to strain rate to velocity to displacement, and I believe it's based on standard deviation with respect to averages in that measure. Now, with respect to the question about reverse strain, was this something?
The reverse strain button in the machine.
I don't think there is a reverse.
Okay, maybe we'll follow up with that question.
There is. From time to time, we do get questions related to looking at diastolic dysfunction, and which could be considered reverse strain. I don't know if that's what the person was asking about. It is possible to look at diastolic function with the software. It's a bit of a noisy measure. The tracking algorithm in Strain is really designed to look at contractility and not the relaxation function. It is possible to do it, but the signal-to-noise ratio of that relaxation phase is not as good as it is in the contraction phase. But if it's something that you're really interested in, I would say, take a look at it and try it.
Absolutely. Well, all those questions, there are more to come, and we will follow up with you. We'll ask Stephen to follow up with these questions. Thank you very much for your participation. We are going to close this on-demand tutorial. Thank you all. Thank you, Stephen, and we look forward to your participation at our next on-demand tutorial or live webinar. Thank you very much. Bye for now.